Is there a pointer? Okay, I mean, maybe.
Okay, it's the first time we use this classroom for the seminars, and we were not well prepared. We apologize. It's a pleasure for me to give you Amy Katz from Boston University, who's basically doing research at the interface between condensed matter and high energy physics. And today he's going to tell us about his latest developments, developing non-perturbative numerical approaches to study field theories, and especially real-time dynamics.
Thanks very much. Fun to come such a short distance. Hopefully, we can start some good collaborations. So I'm going to talk about a whole set of papers with these authors here. The purpose here is to give you kind of more of an overview of the kind of work that we do. And the general theme is us trying to understand how to solve quantum field theory in the non-perturbative regime. So these are degrees of freedom that we think of as arising in condensed matter systems, for example, which are near quantum criticality. So the goal, if you like, is to go back to childhood and see if we could solve the Schrodinger equation, except that the Hamiltonian is the Hamiltonian of a quantum field theory. And so how does one think about solving this kind of equation? And traditionally, the way we think about quantum field theory very often is as a set of degrees of freedom that emerge near criticality. So you have some sort of spin system or maybe some other kind of system of electrons. And we tune this system, or a system of atoms, right? We tune this system to a second order phase transition, and the quantum field theory describes the long distance fluctuations of that system, right? So this has become not just kind of, obviously, this connection is a very profound connection, and not only, of course, is kind of very interesting and beautiful that quantum field theory can describe the physics near criticality, but in a sense, this connection flows both directions in that when we think about quantum field theory non-perturbatively, in practice, the way we think about it is by setting up some sort of condensed matter-like system and by tuning the parameters of that condensed matter system to criticality, right? So even if we're interested in particle physics applications, what we really do when we talk about QCD, for instance, is we write down a lattice system of some sort, and we tune that system to criticality, and the quantum field theory manifests itself there. Yeah.
What about this system?
Second order phase transition. Right, so they have gapless excitations, right, as you approach the phase transition. And though I don't, I can tell you a little bit maybe offline, but very often these gapless excitations, very often if the system has local interactions, then it has emergent symmetries that are more than sort of the microscopic symmetry. So for example, you can get Lorentz invariance, right? And that has to do with essentially with local energy transport. So if you have a microscopic system with local energy transport and it goes to a second order phase transition, chances are it'll actually be relativistic. I can tell you more, like maybe after the talk about this. But the question that I want to ask today, and the methods that I want to kind of present today, is this sort of a different framework, right? So the traditional framework is always to relate quantum field theory to some sort of system near criticality. But in a way, if we're trying to understand truly non-perturbative phenomena, and if our quantum field theory is not integrable, is there another way to understand the non-perturbative physics? Is another way to compute that kind of data?
Make sure I understand the motivation.
Yeah.
Lydian lattice theories are not perturbative quantum field theories, but you're interested in the real-time dynamics.
Exactly.
Got it.
Exactly. And moreover, as I said, Euclidean lattice field theories are this. That it's a lattice theory in which you're tuning to criticality. And so in some sense, it's still, if you want, give you a particle physics slogan, there's an ether. Really, you think about it, right? Like, I mean, you could decide that that's okay. But, you know, if you are asking yourself, does quantum field theory exist without an ether as a practical computational tool? I would say that this perspective is creating an ether, and the ether fluctuates to give you that. Right? But you can ask, you know, does it exist on its own? And so in practice, though, what am I really interested in? Well, you know, as I was already kind of hinting at, very often we see an emergence of symmetry, right? So the microscopic degrees of freedom don't enjoy the same symmetry as the quantum field theory. The quantum field theory typically has additional symmetries, right? They can be translation invariance, rotational invariance, Lorentz invariance, conformal invariance, various flavor symmetries that are not manifest microscopically emerge in the quantum field theory degrees of freedom. And so in practice, really what I'm trying to ask is there a way to capture non-perturbative quantum field theories while preserving these intrinsic QFT symmetries? Manifestly. Yeah. No. It's non-trivial. Yeah, so there are certain, for some cases we understand it well, but in general, this can be quite subtle. For example, lattice translation symmetries can emerge as charge conjugation symmetries in the continuum quantum field theory. So it could be quite a non-trivial map that sometimes is an art form to figure out. So in a sense, I mean, even though I'm not really going to talk much about particle physics applications today, from the perspective of particle physics, it's at least an interesting question because, again, we have particle physics models, in particular, let's say the standard model or chunks of the standard model. Those models or those descriptions we enjoy all these symmetries, translation invariance, Lorentz invariance. There's a full Poincare symmetry, and experimentally, as far as we can tell, those are perfect symmetries. In other words, we don't expect violations of those symmetries. And so it's an interesting question whether or not there's a non-perturbative formulation of quantum field theory that, in fact, manifests as much as possible the actual symmetries of the quantum field theory. But even if you are kind of interested in emergent quantum field theories, for example, you might be building yourself some spin system that I'll talk about today, or you could realize it in terms of cold atoms, and you are tuning the system to near criticality, and your quantum field theory degrees of freedom are emergent, well, then it might still be useful to have a framework which has all the symmetries of the quantum field theory manifest, and then you can think about having a framework that computes the data of the quantum field theory, and then in an effective theory framework, you are adding irrelevant operators to this quantum field theory, operators that are coming from whatever is the microscopic underlying description. So the microscopic data affects these coefficients. And here I've sort of put in kind of cartoonishly like a lattice spacing. So there's some set of operators depending on their scaling dimensions that come into here. I guess this would be like, yeah, that's right. So it should be but delta I minus D. But the idea is that there's a series of operators, and if you understand the quantum field theory, you also understand these operators, and you could systematically parametrize various UV lattice effects, and that way of computing might be more efficient, especially if you're sort of thinking about the thermodynamic limit, right? You have many spins, so you have a large system, and it might in the large system size, the symmetries are a very good approximation, and therefore it may be smarter to think about having perfect symmetries and parameterize the violations. Yeah.
How do you make sure that you get a QFT and what the mean field theory with these symmetries?
What do you mean a mean field theory?
So classical field theory would be.
So yes, I'm talking about a quantum system, which I'm tuning to quantum criticality, not classical criticality. Yeah. So we're interested in capturing the real-time evolution of a quantum system tuned to criticality. Yeah, good. So the method that I'm going to be describing is part of a kind of a family of methods, which, if you like, is really a trial wave function kind of method. So we're trying to solve the Schrodinger equation. We're trying to approximate the eigenstates of the Hamiltonian. And so the way, an approach that you could use, which you could use, of course, not just in quantum field theory, but in many quantum problems, is, well, you first choose a basis to describe the states of the Hilbert space. And, okay, so this is always an infinite basis because the quantum field theory will have an infinite number of degrees of freedom. Then you truncate to some finite subset of this basis. So now you have your matrix and you have some set of basis states, some finite list of basis states. And so now you've taken the quantum field theory Hamiltonian and reduced it to some finite but very large matrix in this basis. And then you diagonalize this matrix numerically, and that gives you some kind of approximate eigenstate. So if you want, this is some sort of trial wave function where you parameterize your wave function in terms of some basis of states. So there are all kinds of versions of this. I'll try to tell you about 2 types today. And the whole question is, how do you do this well? Like, what is the right basis to choose for some particular quantum field theory observables? And the idea is that if you choose your basis well, then it will converge as you increase it, right? So you keep increasing the size of this matrix by including more and more vectors in your basis. And observables, if you've chosen the basis well, then you'll see quantum field theory observables converge.
So, so you're, in this case, you're at every intermediate step, you have a finite dimensional over space.
Yes. Exactly.
Have you thought about if you care about the cardinality of the over space dimensions you go to infinity? Because it's a little ambiguous in the if you have the over space is all of the numbers.
Well, I mean, so you have to choose a basis, which you think is a complete basis for the Hilbert space. And then the question is, are you going to get efficient convergence?
So if there's a jump, right? I mean, okay, so that was going to be my question. Is the Hilbert space jump both when you remove the cutoff and when you remove ultraviolet cutoff, and when you remove, right? It's entirely possible that the domain of the cutoff Hamiltonian, the domain of the limit Hamiltonian will have as their intersection precisely vector 0. That happens all the time.
Yes, that happens. And so we will talk about it. All right. The challenge in this kind of method is basically the fact that you're taking this large chunk of the Hilbert space, you're diagonalizing these large matrices, and the growth in the number of states is quite rapid, right? So here D is the space-time dimension, and so you have a kind of a rapid growth. And so in some sense, it's important to find an efficient basis or an efficient truncation. So even though we've done work, for example, in 2+1 space-time dimensions, most of the stuff that I'll show you today is in 1+1, because again, like, you can push the method further, and you can you can essentially explore regimes of quantum field theory that are where essentially there's no other way to explore them, and therefore it's always a good idea to start with lower dimensional examples. Also, because I think that some of the lower dimensional examples, in fact, can have very nice connections to condensed matter systems. So here's kind of a prototypical thing you might want to do. So here's one of the simplest field theories you can think of. It's a relativistic scalar. It's a boson, and I'm going to assume that it has a repulsive interaction. So lambda is positive. It's Lagrangian. It's a massive scalar. And so, for instance, one possible truncation that you might immediately think about right off the bat is you take just the Fock space basis, right? So you can you put the theory on a circle. It's a one-dimensional system. Now all the momenta are quantized. You take all momenta up to some particular maximum, and you include states up to some particular maximum number of particles, right? And so in this context, this could be a possible truncation. You include this as your basis states. You compute the Hamiltonian in that basis. You get a finite matrix and you diagonalize, right? So this has been a technique that people have used. In fact, I think this particular example might be from the 80s. In fact, was probably the first time that people tried this sort of method. And so this is kind of a typical example. You diagonalize it and you get some set of eigenstates in terms of this basis, and you increase the size and you attempt to reproduce the eigenstates better and better and better.
You just watch the convergence.
Yeah, yes, that's right. You just watch the convergence, and typically the convergence goes as 1 over a power law of these quantities. But of course, the Hilbert space grows exponentially with those quantities, so it's an exponentially difficult problem. But still, you know, you can do this, and you get a lot of information, as I'll try to show you, about the theory, which is kind of interesting. So, what?
That theory has your normalization.
No, this case, it's you just normal order it. Yeah. Yeah. And in higher dimensions, we know how to renormalize. Okay, but there's another kind of maybe less familiar perspective on the Hilbert space, which I think is in a certain sense.
Once you renormalize, it's no longer bounded down.
It is. Okay, let's talk.
You get an infinite mass correction as the wrong side.
Okay.
From
Let's talk separately. Okay. All right. So here there's a different perspective, however, which is kind of maybe a bit less familiar, but we found in some sense, as I'll try to show you, is a more efficient perspective, and I think in some sense a more universal perspective of how one thinks of a quantum field theory, and that is to start with a conformal field theory first, and think of the quantum field theory as a relevant deformation of the conformal field theory. So you take the degrees of freedom of the conformal field theory, and you add to the conformal field theory an operator that grows towards the IR, right? And now you're describing the full quantum field theory, which doesn't have scale invariance, but using the data of the theory that does have scale invariance, namely the conformal field theory. So this framework has a sort of appealing structure because it inherits the structure of the CFT, whereby one has the CFT has a connection between the local operators, so if you like, the observables of the CFT, and the states of the Hilbert space. So CFT has this kind of nice structure which links the observables with the Hilbert space. So it's kind of self-contained, and moreover, because we think that as you go from the UV degrees of freedom to the IR degrees of freedom that include these relevant deformations, you never gain degrees of freedom, right? There's a sort of notion of a C theorem that the number of degrees of freedom only decreases, and therefore this Hilbert space can capture what happens in the full quantum field theory.
Missing something, but here the correction term that you're adding is something irrelevant.
Yeah.
And the earlier thing you were something irrelevant. Is that just because this term is on the other side?
Oh, no, before I was thinking just including irrelevant contributions perturbatively. Right.
This is supposed to be like
Well, I mean, yeah, there's certainly a notion that if you flow from some other set of degrees of freedom, then you're losing these degrees of freedom. One can make that somewhat precise in the case of 1+1 dimensional theories. However, here I mean, strictly speaking, in a context where the full symmetries, say, for example, Lorentz invariance or rotational invariance or whatnot, are maintained. Whereas if you are flowing from a lattice, then the story is a little bit different, right? How you should think about it.
It's not true, or at least it's not obvious that I can write every QFT in this decomposition.
I don't have a proof, but most things I care about, one can do.
Yeah, but I mean, for example, there are CFTs that don't have, I mean, perhaps if we wrote relevant plus marginal also.
Yeah. So, I mean, most theories that I would care about, one can do this. I mean, I don't have a mathematical proof that this is always possible.
No, I think actually it's not important. I think there are other things. One can construct examples where this is not.
Maybe let's talk and tell me what. Yeah.
So in practice, if someone gives you a QFT, do you have any systematic way to make a wise choice of what CFT to start from?
Yeah, that's a great question. I don't think there's a unique choice typically, but there's certainly kind of minimal choices that you might want to make, right? Like you could easily embed QCD into a CFT. You can embed QCD into all kinds of CFTs, and maybe some of them are easier. Present a framework for the Hilbert space that preserves sort of similar symmetries. So it's a little bit a question of judgment how you want to.
Different CFTs are going to be different, right?
Yes.
And the Hilbert states are also going to be different in the QFT you're proving.
Well, the QFT, technically speaking, is the full QFT, right? Including the UV and the IR. Now, of course, you could be interested in something like you might say, I don't care about, the UV. Like if you embed QCD, for instance, into a CFT, then you might say, well, I only care about physics up to a certain scale. But the full QFT is the full QFT. Right. I mean, so you can, the local, you could have different, yeah. So if you're interested in certain fixed points, for example, the full flow, then maybe you can have different local operators that describe the same IR, but it's no different than saying that, okay, I can have different lattice realizations of the same emergent quantum field theory. So the nice thing also about this sort of framework is that the QFT dynamics. So here are, you can describe this operator, the Hamiltonian, and this basis of states which are related to local operators. And so now you have this matrix in this basis. And the nice thing about it is that the entire matrix just depends on the CFT data. So that's because when you're, measuring the matrix elements here, this is diagonal, whereas here you're essentially getting a 3-point function. And so the CFT data, namely the scaling dimensions of operators, which are essentially for a CFT, the scaling dimensions, right, are you measure a 2-point function, it always has a power law fall off, and the power law that you get is the scaling dimension. So that's kind of 2-point function information. And then the 3-point function information is also, because of the symmetry of the CFT, is given by a finite set of constants, which are called the OPE coefficients. So in practice, if someone gives you this data, then the entire Hamiltonian is well defined. Now, although I should right away say that obtaining this data is not at all easy, even for free theories. It's just an exponentially difficult problem. So you always have to come up with clever ways, using a lot of symmetries and formal structure to actually obtain this data. But some of our excitement also about this kind of framework is the fact that very recently there have been all kinds of new techniques for computing this data. This includes both the conformal bootstrap as well as sort of fuzzy sphere techniques, which where these kinds of things can be computed systematically. And so there's a new kind of approach that has a hope of building QFTs from CFT data.
I guess the assumption is that somehow you're writing the relevant deformation in terms of the CFT data itself also, so that you can compute the expectation value of that.
Exactly, because when you put this on two sides, you're just computing a 3-point function, and the data of a 3-point function is entirely contained in these.
And I guess also listen to what you're saying is that there's a nice natural order eigen operator convention that's going to give you a nice function operator.
Yes, that's kind of where we're going with, but right now I'm just sort of parametrizing. This is a way of parametrizing the Hilbert space. All right, so let me come back to this question of efficiency and to the nature of truncation. And I just want to explain sort of some of the difficulties that one can potentially get in one of the challenges. So here again is this example where we truncate on the momentum, right? And we truncate on the particle number. So imagine that you're doing this computation in this 1+1 dimensional theory in this way. By the way, I should note that as kind of promised, when you do the computation this way, you are preserving momentum, right? So the idea is you're putting this theory on a circle. And so in this context where the theory is put on a circle, but then momentum is conserved. So that's one of the advantages of this method is that momentum will be conserved in this method. But I want to try to understand the connection between this kind of way of computing using truncation or using this sort of ansatz for how to parameterize a wave function and perhaps a more standard way that we compute, right? So in quantum field theory, we compute observables, and we typically expand these observables in terms of some coupling. So we have an expansion, and what is the connection between the two, right? So one idea would be that, you know, we compute in perturbation theory, we compute using Feynman diagrams. We compute some observable order in the coupling. And another is we use a particular type of truncation, and we just choose the coupling to be small, right? And I want to understand what is the connection between these two approaches. In particular, I want to understand this connection when we take the volume to be large. So again, we're looking at a particular basis. We're computing within this truncated part of the space. We're computing some observable. And the question I want to ask you guys is, will we recover, if we take the volume to be to infinity, will we recover Feynman diagrams? Would we recover the Lorentz invariant, for example, in this theory? It's a Lorentz invariant theory. Of course, Lorentz invariance is broken by the finite volume. It's also broken by the UV cutoff. But as we take the volume to infinity, so let's say we truncate to, I don't know, 90 particles, and we're trying to recover the one loop Feynman diagram, right? So we're with 90 particles, we take the volume to infinity with some finite UV cutoff. Do we in fact recover Feynman diagrams as the volume goes to infinity? Who wants to venture it? Yes. Yes or no?
In general or for this theory?
For this theory. Like giving you a very concrete theory. It's 5 to the 4th. You know, you've taken 90 particles. I'm asking you, do you recover the one loop, I don't know, correction to the mass as you take the volume?
At fixed cutoff.
At fixed UV cutoff and at fixed number of particles.
But generically no sense.
Yeah, no. The answer is no. We don't. Why? Because of the orthogonality catastrophe. Right? So sometimes we forget this when we think about teach quantum field theory, but Feynman diagrams are kind of a hopeful, you know, wish in a certain sense that we understand what happens at large volumes, right? So the orthogonality catastrophe is simply the statement that if I have the original vacuum, the original ground state of my free theory, And now I've added an interaction. What is the overlap between the original ground state and the new ground state in the presence of the interaction? And it is well known that because you have a local interaction, that the overlap is going to be exponentially small in the volume, right? So in fact, just recovering a one loop Feynman diagram at very large volume is an infinitely, with the standard approach, is exponentially difficult. You need an exponential number of basis states to capture the new vacuum. And of course, this is not special, but truly true just about the vacuum. It's true about any of the eigenstates of the interacting Hamiltonian. So it seems very strange that a perturbative answer, which you think is sort of be in some sense polynomially complex, requires an exponential complexity. I'm also going to remind you why you should have suspected that that's the answer anyway, and that's because Feynman diagrams in a Lorentz invariant theory are themselves Lorentz invariant. However, the boost generator in this bosonic theory is made up of the free part of the stress tensor, the free part of the Hamiltonian density, and also the interacting part of the Hamiltonian density. And this interacting part of the Hamiltonian density, of course, violates particle number. So you could never, in any sector of a fixed particle number, recover Lorentz invariance. Right? That's something important to think about. And so you might ask yourself, okay, but I've sort of been taught that Feynman diagrams are really kind of just a very clever rehashing and reorganizing of perturbation theory in a way that makes Lorentz invariance manifest. But then you can ask yourself, okay, here we're seeing that they're not really the perturbative expansion of the treatment, standard Hamiltonian treatment. And so you can ask, are Feynman diagrams really the perturbative expansion of what kind of Hamiltonian framework? Not of the standard one. And Weinberg answered this question back in the 60s, and he discovered something called like-code quantization. So this is the thing I want to explain next in kind of a more modern language. So there is a way of organizing your thinking about a quantum field theory in such a way that the volume, this exponential difficulty with the volume just never appears. And indeed, in that way of thinking, reproducing some particular Feynman diagram becomes a polynomial problem. So let's take a Lorentz invariant theory in a circle of size L. And what we're going to consider are states that are not of zero momentum, but states that are moving on the circle. And we're going to take the momentum to infinity. So these states are moving increasingly rapidly on the circle. So in a Lorentz invariant theory, we expect the following structure for the spectrum, right? There's going to be the spectrum will be discrete because we're on a compact space. And so we're going to get some set of eigenvalues, and we're going to have a momentum, and we're going to keep increasing this momentum. And it turns out that what's interesting to consider is the so-called light cone energy. So this light cone energy is the difference between the Hamiltonian and the momentum operator. And we note that this difference, the eigenvalues here, what happens to this difference is that the leading terms cancel, and in fact, the eigenvalue starts tending to zero. So as we boost more and more and more, we find that more and more of the eigenvalues fall below the sort of typical energy on a circle, that is to say 1 over L. And so I want to show you this in a kind of example, which is atypical for quantum field theory description. However, it is an example that is very interesting from the perspective of condensed matter and systems that one can engineer in the lab. And it's related to something called the Ising field theory. So the idea is you take the Ising CFT, which is really just a free fermion, and you perturb it with something called the sigma operator. This is a theory that turns out to be integrable. It's a famous E8 theory that Zimological solved. And for those of you more condensed matter background, this is nothing but the kind of quantum critical set of degrees of freedom of the familiar model where you have spins coupled to each other, and you take the transverse field Ising chain, you tune the system to criticality, and then you perturb with a small longitudinal field, right? So I believe that the full spin chain is not integrable, but the low energy degrees of freedom are. So this is an interesting theory. Of course, the Ising CFT is nothing but a free massless real fermion. But what's interesting about this theory, I think, is that in some sense it's non-Lagrangian, in the sense that this sigma operator is quite complicated in terms of the fermionic fields, right? It's not a simple operator that you can describe in terms of the fermionic degrees of freedom. In particular, in this theory, the fermionic field doesn't obey some simple equation of motion. So, but this is a very interesting theory, and a theory that people have realized experimentally, in fact, in the lab. So, so it's kind of a fun example to consider. And so here's the data for that theory. One could compute in this theory the spectrum, and again, take the large momentum limit, and you see that this pattern that I was advertising. So here's the this light cone energy, and here is the x-axis is momentum. And as we have this sort of sparse discrete spectrum, but as we crank up the momentum, the eigenvalues seem to all crash down. And so there's a kind of natural pileup of eigenvalues that one gets as we're boosting the system. And so here's why I want to suggest that this kind of large P limit is in fact a kind of effective theory. That's because we have a pileup, right? And all the spectrum is sort of crashing to be less than the characteristic scale 1 over L. And so it makes sense maybe to guess that given this pileup, that the natural effective field theory degrees of freedom are states which start out with having no light cone energy. So what are those states? Those are, so for example, in this model, you have a fermion, there's left movers and there's right movers. And so these states that have the massless fermion has left movers and right movers, and these states are the states that are made entirely of left movers. So not left movers and right movers, but just left movers. So this is already kind of a signal that in some sense, thinking of things in terms of a CFT is useful, because if these are the natural effective degrees of freedom, those effective degrees of freedom naturally live in a 1 + 1 dimensional CFT. 1 + 1 dimensional CFTs always have a chiral sector. They always have a sector which start with no light cone energy. They're just left moving particles, right? So the idea is that these are the natural degrees of freedom of the effective theory. And the conjecture that we have is the following, that there's an effective light cone Hamiltonian. So it's an effective theory. We have to, in principle, compute this effective Hamiltonian. It doesn't act on the full Hilbert space of the theory, but only on these chiral states, only on left-moving states. However, it has the exact same physics as the large P limit of the full theory. That's the idea, because the entire spectrum is crashing into P plus equals to 0, and any states that contains, let's say, right movers is sort of infinitely far away. It's an energy is infinitely far from what happens here. And so the eigenvalues of the full Hamiltonian, or the full light cone Hamiltonian, become just the eigenvalues of this effective Hamiltonian. And if we could derive, if someone gives you this effective light cone Hamiltonian as a gift, that's already a huge efficiency, because the claim is that you can find the exact same physics, but instead of having a Hilbert space that has both left and right movers, you have a Hilbert space that is exponentially smaller. right? It has only, let's say, left movers. So I'll give you, I mean, we don't know how to compute this like an effective Hamiltonian in all cases, but I'll give you some features and I'll show it to you in the examples that we, certain examples, including this E8 theory example. So the idea is you start from, again, a CFT and some set of relevant operators, and the large momentum limit looks like this. It's a set of operators that act only on these chiral states, and a Hamiltonian that has a non-trivial dependence both on the original couplings that entered here, as well as the vacuum expectation values of operators. These vacuum expectation values of operators, for example, know something about the phase the model is in. In a sense, you can think of this as kind of similar in spirit to what you do when you have weak coupling. When you have weak coupling, for example, and your theory is in a double well, say it goes through a phase transition, what happens is that you don't fluctuate around phi equals 0, right? You compute, semi-classically compute the new VEV, and the new VEV enters as a parameter in your Hamiltonian. So now you gain, like, say, a phi cubed term, and the phi cubed term depends on the VEV of the field. And what I'm trying to say is that that kind of physics is more general. So we seem to be finding evidence for that even if you don't have a Lagrangian. The interesting thing here is that boosts, which previously I emphasized to you, depend on the interactions, now do not. So in this infinite momentum limit, the actual Hamiltonian is actually obeys the Lorentz algebra with the CFT boost generator. Not the fully interacting boost generator including, but just the CFT boost generator. So whereas previously boosts were non-trivial, you could not in any finite subsector of the Hilbert space recover Lorentz invariance. Here you can. It's the boost is simply kinematic. Yeah.
Where you have the index as J for the expectation value to 1 point function of the operator.
Yeah.
So does it mean that each of these dipole lambdas depend on expectation value of many other operators?
Yes, so this expectation value, as I'll show you, depends not just on lambda, it could also depend on the volume, but in principle, they depends on the dimensional couplings. But in the infinite volume limit, you can think of this as depending just on all every one of these relevant operators is dimensionful, and so the new couplings depend both on the couplings, original couplings, as well as on the VEVs. Just like in a double well potential.
Can I think of the obstruction? I mean, if I have a Hamiltonian, of course, you would think I can get a Lagrangian from expected transformation. The obstruction is the fact that the conjugate momentum is 0? Or?
To conjugate momentum to what? Sorry?
I mean, in the Legendre transformation, if you have 8, so you can get L with PQ dot.
Oh, yeah. Sure.
Yeah. So in this case, it doesn't work because the momentum is 0.
That's right. And the other thing I should say, I mean, which is kind of an obvious corollary of this, is that if the Lorentz algebra is realized in terms of this effective Hamiltonian and the original, this sort of CFT angular momentum, that it is in fact a CFT vacuum that is the eigenstate of the effective Hamiltonian. So the vacuum does not change. So it's already telling you that all these pesky factors of volume are going to disappear. However, it doesn't mean that the vacuum structure is gone. It's sitting secretly in here. Again, it's no different than what you do when you're doing perturbation theory and you're shifting the VEV semi-classical. Now, we don't know how to compute this effective Hamiltonian in all cases. So what we know, we can certainly do the mechanical exercise, kind of the way I was showing you with the data, where numerically I can compute the effective Hamiltonian. So if I literally take the theory at different momenta and I increase the momenta and I integrate out, let's say if my effective Hamiltonian is acting on the left movers, I integrate out the right movers. I could do this numerically. but that requires me to solve the full theory. And there is certainly like a formal expression I can write down for this effective Hamiltonian, but all the power only comes if I can write it down from the very beginning, because then I don't have to include all these additional degrees of freedom. So there are all kinds of cases where we can numerically compute it, but it only becomes interesting if you could analytically write down an expression. So I'll tell you a particular class of examples where that's possible. And that's when you add a single relevant operator, and the dimension of this relevant operator is quite relevant. So it's like you could have, relevant operator means that the dimension is less than 2, but here I'm going to assume that it's less than 1. And this is the form of this effective Hamiltonian. So as promised, it depends on the product of the coupling and the VEB of this operator. So notice it kind of has the right dimensionality. And it remembers, interestingly, what the volume is. But then you have an expression which is manifestly boost invariant. In terms of an object that is perhaps unfamiliar for some of you, but if you are a CFT person, then this is a very natural thing. It's sort of the inner, comes out from the inner product. You take an operator, you multiply it by its scaling dimension, and you take x to infinity. So this is a very natural operator in the context of CFTs, meaning that if I were to compute the matrix element in my chiral states of this product of OR infinity, this is a well-defined amplitude in the context of CFTs. However, it's already interesting that there is this CFT-like structure. So we already saw that CFTs are somehow preferable because as you're boosting, you're getting closer and closer to P plus equals to 0. But here we're also seeing that on top of it, the very structure of the Hamiltonian suggests that you should be thinking of the operator as living in the CFT Hilbert space. Okay, so we know, and now I'm just going to tell you what our truncation is and then show you some results. So as I said, it's not always clear that the Fock space basis is the most efficient. And instead, these kind of idea of looking at the basis in terms of these chiral CFT states, that seems to be kind of the more efficient way of thinking about it. And so in any kind of 1 + 1 dimensional CFT, there's a set of operators, which are kind of chiral operators. So what are these? These are basically fermionic fields with which are describing only the left movers, let's say, with derivatives of them in the case of the easy model. So this is the kind of operator that you write down. These operators have an inner product. So they have an orthogonality to them. And one can compute the Hamiltonian I just showed you in this basis. And our truncation then becomes, we only consider operators, right? So they have a scaling dimension. So this is just the Fourier transform of the 2-point function, basically, the Whiteman 2-point function. And the truncation that we're suggesting is that we only keep operators whose dimension is below a certain maximum dimension. So this is our truncation. Why do we think it converges? We don't really have a proof, but it is, for those of you who are familiar with holography or with ADS CFT, this is a very natural conjecture given how ADS geometry describes states in a context of a CFT perturbed by a relevant deformation. So here's the results, for example. So here's again, we're starting with the Ising CFT. So this is a free massless fermion, and we're adding to it this kind of, from a field theory perspective, a somewhat exotic operator. Our claim is that the effective Hamiltonian is simply this, a well-defined operator. We can compute its matrix elements in our basis, and then we can go on and measure. And because this is this famous E8 integrable theory, we could compare it to integrability. So we can measure all kinds of time-dependent, non-trivial things. So for example, we can measure a form factor. So this is an operator between two of this theory has 8 bound states, that's like, which are organized in this E8, using this E8 symmetry. And here is a particular form factor. Again, boosts are, momenta are continuous for us, right? Because it's a boost invariant. It's a system in infinite volume, which is boost invariant. And so we can actually parameterize in terms of this invariant, these form factors, and you see that they compare very favorably with integrability. So these are sort of measurements of the inside of some particular state. And you see that we agree with integrability. Here's another observable, the real-time two-point function. So you can take the stress tensor, take its real-time two-point function, Fourier transform it in frequency space, and integrate the frequency up to some maximum mu squared. That is a particularly interesting quantity because it's homological C function. This function always increases as you go to higher energy. So the integral is always bounded by the number of degrees of freedom of the theory. And so this is what it looks like numerically. So again, we have the results of integrability, and we have in red the results of our numerical computation. And you see that the agreement is pretty good. And even, we can see that at high energies, it asymptotes to a half, which is in fact the correct C for free fermion. So we can compute all kinds of quantities. For example, the contribution of these various bound states. This is C1, this contribution is C2, and there's another one, C3. The various masses, again, these are the results of our numerics. These are the results of integrability. So the convergence is pretty good, and there are only 470 states here. So if you know anything about these types of computations using, I don't know, Fock space basis or some other basis, it never comes close to this, and people typically talk about 40,000 states. Yes. Sorry? Oh, so this particular theory is integrable. What that means is that it only has 2-to-2 scattering. So there's no particle production. And people know the precise form of the S matrix for any one of these particular bound states. And from knowing the S matrix, you can compute form factors, you can compute two-point functions, you can compute everything. Yeah. Yes. Okay, so now that we've got sort of the great homologic of agreeing with us, we will venture into uncharted territories. So now I'm going to show you the results for a theory which is not integrable, but again, a theory that is very appealing from the perspective of condensed matter. Indeed, it's essentially the same type of chain, but instead of just having this parameter here, I'm detuning from criticality.
All of these cases, you really affect like
Yes, that's right. So I don't know. So here's an interesting particular example. So again, like as I've emphasized, the light cone effective theory depends on the phase, right? Part of the data of the light cone effective theory is the VEVs associated with different phases. So in this particular theory, it's kind of interesting. I can explain like offline later. We don't know what the effective Hamiltonian is in both phases. We just know it in one of the phases. We have numerical proof that it should exist in the other phase, but we don't know how to write down its form in some kind of nice compact way. However, in the case of the symmetry broken phase, which in some sense is the more interesting one, this is it. So there is the term that we already discussed, plus this new term that has to do with this term, by the way, the epsilon is just in terms of the easing operators, this is the same as epsilon, but in terms of kind of field theory, this is nothing but just a mass for the fermion. So it was already long-term known, long while ago that if I turned off G, everybody knew for a long time that kind of the light cone effective description for a massive fermion is this one here. But the new ingredient that we've added is noticing that in fact the combination of these two terms is all that one needs to describe the symmetry broken phase. The symmetry broken phase is a cool phase. I mean, in terms of a kind of Landau picture, you can think of it as we are if it was perfectly spontaneously broken, we would have a double well potential with equal, equal wells, which the fermions of that are just the kinks that tunnel from one vacuum to another, and therefore the force between them would be zero. But if you detune a little bit, which is equivalent to adding this sort of Z2 breaking coupling here, so adding this kind of term here, then you've detuned this, and therefore suddenly the kinks develop an attraction, right? Because being in the wrong vacuum is disadvantage. It's a disadvantage, right? So if you go from a kink, anti-kink, want to pull together to minimize the wrong vacuum. And so what's cool about this model is that in the broken phase, it's a confining model. It has much of the kind of physics as QCD.
If the turn of M, I find the logicals.
Sorry?
If I said M equals to 0, this is the logical.
Right. But in, with both of these on, it's a non-integrable theorem. I mean, we can't,
I'm just confused about the 1 plus M.
sorry?
So this,
Oh, this thing is the lattice version.
yeah, no. Why is there 1 plus M? If I set M to 0, this
Yeah,
second.
No. It's because in the lattice theory, the M equals 0 is in fact what the Jordan-Wigner corresponds to a massless frame.
that term was there.
It was always there. Yeah, sorry, it's, again, this is something that I think condensed matter people know in their hearts.
Yeah,
And
sorry.
but I would also be confused, but that's how it works in this particular model. So now the fun thing is that we could repeat the kinds of measurements. For example, again, we could look at the spectral density of the stress tensor, right? So this is this thing. It depends on some factors here that carry the boost, and then there's a Lorentz invariant piece, which depends on the Lorentz invariant combination, and we can actually compute it. Like this is like, I don't know, computing E plus E minus to hadrons. So here's this is what it looks like. So here is this mu, this Lorentz invariant direction is this mu here is this direction, and here I've shown you kind of the 1 over the coupling. So eta is standard in the literature. It's 1 over the coupling. So coupling equal, so mass equal. So the homological point is here. It's this 0 coupling right here. And as we go this way, the coupling is going to 0, right? So weak coupling is essentially that way. Strong coupling is here, but this is also an integrable model. So this is the actual spectral density, right? So it's kind of neat. You can see the physics. You can see the stable bound states, right? So as we said, there's a linear potential, and this linear potential causes these fermions to confine. So there's for a given coupling, we predict what the bound states are. And then what's interesting is that given the mass of the lowest bound state, this is the 2-particle threshold. So naively, you would have expected that up here we just see a mush. That is to say, now these are not bound states anymore, they're resonances. The coupling is order 1. So right here we have strong coupling, yet we seem to be seeing these incredibly narrow resonances. I mean, it's not in disagreement with, this kind of thing was suggestive by earlier numerical results. So we don't think that we're crazy. However, we're, I think, the first people to actually measure these widths in this model. And it's kind of cool, I don't know if that you can have a theory with very strong coupling, but somehow incredibly narrow resonances.
Remember the dotted line, the yellow line?
The yellow line is just twice this. Yeah. Yeah, so, okay, so this is kind of an interesting, so this is the kind of thing that you can compute. All right, let's see, how much time do I have left? Not much, is that right?
Not much, but
Okay, how much do I have since I started late? Can you give me 10? Okay, so I want to tell you kind of, sorry? Yeah, there were a lot of questions. So let me give you, so mostly I wanted to explain kind of, but there's a interesting regime where we I think, in some sense, ventured for the first time. And these are high energy quantum field theory states. So these are states whose energy is much, much bigger than the typical mass of particles. And what's interesting is that people have, especially in the condensed matter literature, explored the idea of emergent temperature. So how is it that temperature emerges in closed systems? And so it's interesting to try to understand whether in this kind of framework of quantum field theory, we see the presence of ideas that are the kind of ideas people had in mind for how temperature emerges in closed systems. Okay, so there's an old argument by Srednicki, but I don't have much time, so I'm not going to review it. I'm happy to talk about it offline. But I want to just say that Srednicki concluded something which I think is quite profound, which is that if you start with some initial state, whatever it is, with some kind of average energy, and you evolve in time some operator, if the system should reach equilibrium, then the system is closed. Like the idea is what are the consequences for a quantum mechanical system if any initial state, if you evolve it in time, should reach some kind of equilibrium with some kind of density matrix. And so essentially just going through kind of a one-line argument with some linear algebra and knowing that chaotic systems, so systems that reach equilibrium are believed to be, for all initial conditions, are believed to be chaotic. Chaotic systems are supposed to have level repulsion. We'll talk a little bit about that. And how is it that it's mechanically possible given whatever initial conditions to reach equilibrium? And Srednicki concludes that something quite amazing, that the expectation value of some local operator, some operator that has access to just a few degrees of freedom in some complicated eigenstate of a many-body system should already be to exponential accuracy almost the equilibrium expectation value. This is called the eigenstate thermalization hypothesis. And if you further extrapolate the meaning of this eigenstate thermalization hypothesis to the idea of large volumes, then these high energy states, which have a finite energy density, should have an equivalent temperature, right? So kind of large volume. In the large volume limit, the microcanonical ensemble is the same as the canonical ensemble. So there's this idea that if you measure a local operator in some very complicated state, then the expectation value of this local operator should be approximately thermal. So it's a very profound observation that already says that the kind of what is quantum ergodicity. It's the fact that any eigenstate, that is to say, which is already kind of a stationary state of the Hamiltonian, is already a thermal bath. If you make a local measurement in this room and you don't have enough access to all the degrees of freedom of the gas, then you think that you're in a thermal bath. And there's been a lot of interesting and amazing work by many people to verify this for some system with a fixed number of degrees of freedom, like and particles or spin systems. And what we are trying to understand is in what sense is this true for quantum field theory? And the reason that this is an interesting question is precisely because it's not obvious how to think about it. Like QFT data is not quintessentially discrete, except for the case of CFTs, which I mentioned. The data is there as discrete. And the QFT high energy data can only be computed numerically in practice. And by discretizing the QFT, right? Because you have to put it on a computer. And this data will always be partial and approximate. It's not at all obvious that whatever discretization you've placed on this QFT in order to put it on a computer will obey eigenstate thermalization. And also, the question is, okay, if a typical state, if you probe it, looks to you like a thermal bath, are there non-typical states? Are there states that are that don't behave like a thermal bath? So if you had them in your initial condition, they wouldn't thermalize. They would keep some notion, some memory of the initial system. Okay, let me skip this. So it's kind of a effective theory perspective, but I just want to say maybe one thing, big picture wise, that one of the things that I think is very interesting that's also a recent development is the idea that, okay, suppose I measure a one-point function and I see that a lot of these one-point functions look like they're thermal, then now I have a natural prediction, like an effective theory prediction for what two-point functions are at long distances and at long times because we believe in hydrodynamics. Hydrodynamics is in some sense the most robust effective theory we know. It's supposed to always apply. And it's very interesting that we have different predictions, right? So, you know, you shake a system and you excite like some high energy state and you are at very low frequencies and low momenta, you're supposed to see some hydrodynamic pull. You see a sound wave with some kind of this diffusion constant. So there's some form that this has. And very recently, people have come up with really an effective theory framework whereby all these structures are understood in some set of operators, very, very much like an effective theory description of any kind of long distance fluctuation. So this is something that I think is a very interesting question. How do you see hydrodynamics emerge? And it's something that is very difficult to get from Euclidean lattice. It's something that is, in some sense, this kind of approach of looking at real-time evolution in a high energy state. This is the only kind of method that has a chance of seeing that. And moreover, if you have a lattice system, lattices at some level will always violate momentum conservation, right? So it's going to be much harder to see hydrodynamic modes when you know that, for example, the momentum is being eaten up by the lattice. Okay, so what I'm going to do is just show you my last slide of our numerical test. So we're trying to figure out, is it true that operators have thermal expectation values? And this, I guess I'll skip the random matrix theory because I don't have time. So we're doing this in the 5 to the 4th in 1 + 1 dimensions. We are using, again, our basis of states which are created by essentially these kinds of operators. So these are the chiral, again, we're parametrizing the chiral degrees of freedom in a CFT way. So these are, in some sense, you can think of as polynomials on the Fock space, but some very particular ones. And so let me switch to telling you what I think is the upshot, which is this. Okay, so what we did here is we decided to test eigenstate thermalization. So we're numerically computed these states. And then we went and we measured some operator. In particular, here I'm showing you d5 to the 4th. Now, how is it that we can test eigenstate thermalization? We can test it because when we are at very high temperatures compared to the relevant deformations, that is just described by the CFT. And therefore, the expectation value of this operator is entirely given in terms of the CFT data. It depends on a coefficient that we know from the CFT because it's just a free scalar, and a power of the temperature, which corresponds to the dimension of this operator because it's scaling variant. And so we go out and we measure these. And so there's some regime over which we think, so I divided it by, this is supposed to go as temperature to the 4th or the energy density squared. So the first thing is, does it flatline? And indeed, there's a kind of a regime, natural regime where it flatlines. It flatlines at the same point, independent of the coupling. Again, this expectation value shouldn't really care about the coupling. And so one can check, first of all, that there's universality. And second, one could do a more careful check, which is that there are certain combinations of operators in the CFT which have a 0 thermal expectation value and up to corrections. And here we see precisely that. We see these two operators having an expectation value that that's agree more and more as we increase the temperature, as we increase the energy density. So, and even more, kind of more delicately, right? Like we can look at the difference between these two operators. So this difference is supposed to be 0 in the CFT limit, but when the coupling is very small, the dominant conformal breaking effect that comes from here should just be from the mass itself. And the thermal, if I just look at expectation value of a massive scalar, then this is this dashed line. So we see, so the free massive theory, we have a like analytic prediction for what its expectation value should be as a function of energy density. And we see that our data, as we increase our truncation, agrees better and better with this line. So we really see an emergence of temperature. Right.
What were the numbers, measure? 30, 35?
Just our truncation. Like truncation parameter of 30, 35, and 40.
The number of the dimension of the basis, or is it-
No, the basis is quite large. It's like 40,000 in this case.
Oh.
Yeah, here, because we're looking at very high energy states, right? Right. Yeah. Yeah, I mean, I guess I skipped the slide. There was some slide here. Just to show you what, this is what, these are how many states we roughly have. So here we're just trying, the only point here was just us trying to understand over which regime of energy density we should trust our states, right? Because in the UV, we have a UV cutoff and we run out of states, and in the IR, there's some IR effects. But there's clearly some band over which the growth in the number of states matches what we expect from Hardy's formula. And so it's only in that regime that we, that I trust the plots that I've shown you, but it's precisely like, this is the regime. Flat lines where there's universality and so on. Okay, that's all I have to say for now. I have other stuff, but I'm happy to show you this offline. So maybe I should just go to my conclusions. So this is kind of a new regime, and we can compute data that we weren't able to compute ever before. We can understand, for example, how temperature emerges in quantum field theories, and using the fuzzy sphere that we are working on right now, we hope to update everything that I've shown you in 1+1 to 2+1 pretty soon. Thanks. Sorry for running over time.
I have a quick question, just to make that. You have tons of examples, lots of things seem to be working. I mean, I feel like one of my main takeaways here in this, it's just obvious that the Hamiltonian thing and the real-time dynamics is simply different from what people do with lattice. So I appreciate the conceptual point. But the point about light cone, you motivated in terms of sort of these states coming down and sort of the truncation being better in light cone quantization than in traditional like time foliation. Is another way to understand that when you foliate in time, that basically Lorentz boosts archisymmetry of the theory in a sense that
Yes.
takes you from one.
Yeah.
If you and that goes away in light cone, you have all of the symmetries that you hope for.
Right. I mean, like at least where. Let me just be very clear. I mean, the full subtleties. I think it should work the same in higher dimensions, but all just to be conservative, all of our kind of both numerical and analytic experiments are in 1+1 dimension, and there you just recover. There's a single boost, and you can just show that you recover that.
And I mean, I guess I feel like one of the takeaways, if you were to do it in higher dimensions, you would want to choose a quantization that respects as many symmetries as
Exactly.
possible. If you foliate the wrong way, all of a sudden boosts are not
Right.
Definition of a symmetry is a non-trivial operator on the Hilbert space.
Exactly.
Hamiltonian,
Right.
do not.
Right. So for example, just to advertise, since just to show you, this is our data in 2+1 dimensions. So we really can do 5⁴ in 2+1 dimensions. The Hilbert space goes more rapidly, so we can't go to such high truncations, but with only, in some sense, 550 multiplets, there's a continuous variable that we still need to discretize. So in some sense, that it's not 100, it's not like we have 550 states, but the Hilbert space, this continuous variable, like the Hilbert space doesn't grow exponentially with this continuous variables, whereas it does with this parameter, right? So with only 550 conformal multiplets, we could find the critical point of 5⁴ in 2+1 dimensions. We see universality. We can read off a critical exponent. It's not super precise, but we understand it. Whereas to get the same kind of dynamic range would requires box space basis, like an estimate from people who thought about it is that it's kind of, we're talking billions of states. Yeah. And as far as I know, there isn't even kind of a DMRG version of this, right? So as far as I know, we are the only people who have some kind of dynamical results in a kind of large volume version of a 2+1 dimensional quantum field theory.
Supposing that this were a much more general technique that applies in many dimensions to many different cases. I
Yes.
feel like the principles that you're encouraging us to take away are choose a foliation wisely that respects the symmetries of your theory, perturb around CFT, and then check whether the states are sufficiently coming down so that you can truncate any infinite volume.
Exactly.
Those are the principles that in this case happen to be light cone and.
Exactly.
Okay.
Right. So, my next would be to-do list is check this for a bunch of examples, let's say, on a 2 torus and see that this actually is realized. But yeah. Is it related to a set of 2-point functions? Yeah, so I mean, I would say no. I mean, the 2-point functions, of course, you could diagonalize it. I mean, it's a CFT, right? So the nice things about the CFT is precisely that, you can the 2-point functions are diagonalizable, right? So let me just go back to, I don't know, where did I have a slide on the degrees of freedom, blah, 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 right? Yeah, where is it? Okay, here, right? So this is this thing, right? So, these operators can be very complex. There's some sort of polynomials and derivatives on fields, right? But there will always be some basis in which this is delta ij. And that's the starting point. And in fact, that's precisely why we can even start, right? Is that we have a different kind of basis of the Hilbert space, and in that basis, we can compute this. Yes. Yes. So in the infinite momentum limit, that is the exact commutator. Yeah. For finite momentum, yeah, then this is not the right, in fact, in our paper, we compute even corrections to this as momentum becomes large. Numerically, sometimes it's useful, but because we have to figure this out. But in the cases that we understand, yeah, then the strictly infinite momentum limit is the answer. Or this is the kind of answer. Maybe like I would say in examples that we understand, this is literally.
Yeah, so before we wrap up, I just want to make sure that anyone in the audience, if you have a question, you have a chance to ask. Please unmute yourself and ask your question. Any question? So why don't we wrap up here and then we continue. So let's take Ami one more time.